Hello dear students, let us continue our discussion on linear programming problem. We have already seen the graphical solution, but if you observe carefully, in all of the graphical solution we had only two variables, right? Something like x plus twice y maximize z equal to x plus twice y subject to some constraints, okay? But we did not do any problem involving three variables or four variables. Okay, so why didn't we do this? It's simply because it's difficult to draw graphs of three dimension, even for three dimension is very difficult, but for four variables it's not possible to draw for us. Okay, so that's why the graphical solution that we talk about, it works only when there are only two variables given in an LPP. Okay, only then we can solve it graphically. Okay, so it's quite simple because we just have to draw straight lines and mark the regions which are given by the straight lines. Okay, so in general an LPP may contain hundreds and thousands of variables. Okay, so the graphical method is not practically feasible. So that is why we need a more theoretical approach, right? A more theoretical approach to solving LPP or to the LPP theory, okay? Or say to LPP, right? Means we need to build up a strong theory which will help us to understand the solutions for various cases, okay? Even for large number of variables. So you see, in general an LPP can be written as because there may be many variables. Okay, so I do not know how many variables are there. So in general I can write an LPP as maximize or minimize. Okay, so let us write it in two parts. A maximization LPP. Okay, maximization LPP can be written as, say, maximize z equal to some number c1 into x1. Okay, suppose x1, x2, xn, they are the variables, right? So in general I can write this as c1 x1, c2 x2, c3 x3. Okay, so that way up to, say, something like cn xn. So we can easily write it this way, subject to some constraints. Okay, subject to the constraints. So I do not know how many constraints are there. So in general I will assume that there are m constraints. Okay, so for the first constraint I write it this way: a11 x1 plus a12 x2 plus a13 x3 plus dot 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 up to a1n xn. This is less than or equal to, or it might be equal to, or it might be greater than or equal to, say, some number b1, right? We have seen several constraints where this sign is less than or equal to, some other constraints where the sign is greater than or equal to. We have also seen the constraints where the sign is exactly equal to. Okay, so in such situations, in general setup, the sign can be anything. Okay, so this is our first constraints, right? The second constraint, let us write it as a21 x1, okay, a22 x2, a23 x3 up to a2n xn. Okay, so this is also less than equal to or greater than or equal to, means there are three possibilities here, right? So this is the second one I have written. So in general I can write the ith constraint as ai1 x1, ai2 x2, ai3 x3 plus dot 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 up to ain xn. Okay, less than or equal to, greater than or equal to, say, bi. Okay, so this is in general the ith constraint. So for I equal to 1 I get the first constraint, for I equal to 2 I get the second constraint, okay, like that. So see, we actually require two indices, two index, okay. One index is not sufficient, because we need the index for the ith constraint and as well as the ith jth variable, okay. So a11 is the coefficient of the first constraint, a11 is the coefficient of the first variable in the first constraint, okay. Say a22, it is the coefficient of the second variable in the second constraint, okay. So that's why we need, actually naturally we need two indices to denote these things, okay, right. So all these are linear, right, c1 x1 c2 x2. So this c1 c2 c3, they are called cost, okay. These are called cost, just as we have seen in our formulation that the objective function basically it gives us cost or profit, okay. So in general they are called, they are given a name cost, okay. So x1 is the cost of the c1 is the cost of the variable x1, c2 is the cost of the variable x2, okay, like that, or corresponding to the variable x2, right. So c1 c2 c2 up to cn, that will be called as cost vector, okay. And the last one here, it will be m1. Suppose we are supposing that there are m constraints, so it's a m1 x1, a m2 x2, a m3 x3, plus that way it will go up to a mn xn, okay. That is less than equal to, greater than or equal to bm, okay. So in general we can write LPP in this particular form, right. So naturally you see something comes up in our mind that if we collect these coefficients, we can easily write these equations in form of a single equation or inequation using the concept of matrices, okay. Matrices which you had learned in higher secondary as well as your degree classes, okay. Matrix, we can easily write this thing as a matrix. So let us try to write this as a matrix. So what we have, maximize z equal to, so how do I write it? I will write this one as this is the matrix of variables, okay. This multiplied with c1 c2 up to cn, okay. So this is a one row n column matrix, this is a n row one column matrix. So these two can be multiplied by matrix multiplication. This is nothing but c1 x1 plus c2 x2 plus c3 x3 plus cn xn, okay. So the cost, this objective function, we can write it as cost matrix or cost vector multiplied by the vector of the variables, okay, subject to the constraints. So these constraints also, you see, we can write it as a matrix a11, a12, a13, okay, that way a1n, this is the first row, second row is a21, a22, a23, okay, that way a2n, okay. So in general it is ai1, ai2, ai3, okay, dot up to a-in, and the last one we can write it as am1, am2, am3 up to amn, okay. So this gives us the entire matrix multiplied with x1 x2 up to xn. This will give us less than or equal to greater than or equal to, okay. But when we write this part, we have to be careful. We are combining all the equations or inequations or constraints together, okay. So here we cannot write this thing, okay. It has to be exactly same, otherwise I cannot combine, okay. So if it is something like x plus y less than or equal to 2 and twice x plus 3y greater than or equal to 3, so I cannot write it as a matrix equation in this form, 1 1 2 3 multiplied with xy is less than or equal to 2. So that is incorrect, because The first one is actually less than or equal to, the second one is greater than or equal to. So in order to combine, actually we have to convert everything to the same symbol, either it is less than, or it is greater than, or it is equal to. Okay, so only then I can combine, otherwise we cannot combine. Okay, so here I am putting a question mark. The way of writing this is this, but we have to decide something about this one, the constraint less than or equal to, or greater than or equal to, which one we will take. Okay, so that thing we have to decide, and this is b1, b2 up to bm. Okay, so this first one, this coefficient, so this is actually called matrix of coefficients, or coefficients matrix, coefficient matrix. Okay, so this is an m by n matrix. This is multiplied with the matrix of order n by 1. So if we multiply these two by our higher secondary knowledge, we will get a matrix of order m by 1, which is the this matrix. Okay, so this is called the requirement vector, or requirement matrix. Okay, so this one is the cost matrix, cost vector. Since it is only one row, we say it is a vector. So it's cost vector. This is coefficient matrix. This is the vector of variables. Okay, vector of variables, and the vector on the column vector on the right hand side, that is actually called requirement vector. Okay, so that is the thing. So that is how we denote a general LPP, but of course we have to decide about this constraint. Okay, what we can do. So we will see this as and when necessary. Okay, so in order to analyze, so from this idea itself you can see, or you can understand, that in order to analyze LPP we need actually the help of matrices. Okay, we need to work with matrices, we need to work with this n variables or n tuples. Okay, so we need some linear algebra here. Okay, so some linear algebra for the honors course, it was done in the first semester when you did this higher algebra. So there was something about linear transformations and operations on n tuples. Okay, the ordered n tuples of real numbers. Okay, so we will basically require those simple concepts. Okay, so not very hi-fi linear algebra. We will just require some simple concepts which I am going to discuss. Okay, so you see the set of real numbers here. You have this is our basic set. The numbers that we choose are from the set of real numbers. If we write something called r square, then how do you so here in the set of real numbers we have addition. Okay, if we are given two real numbers, then x plus, this will imply that x plus y is in R, right, and x into y, this is also in R. Okay, or let me write it in form of linear algebra. If we are given two elements x and y in R, then the element x plus y is in R. Okay, sum of two real numbers is a real number. Okay, so this concept is basically a fundamental concept. Okay, we know how to add two real numbers. Okay. And if you are given alpha in R and x in R, then their product alpha x, this is also in R. Okay, so this alpha we term it as a scalar. So it's a real number actually. So for the set of real numbers, this scalar alpha and this vector x, they are the same thing. Okay, so alpha into x, this is always in R. So this product will be called scalar multiplication. Okay, scalar multiplication, right? Okay, so in R square, what is R square? R square is basically the set of ordered pairs of this real numbers. Okay, so R square is basically R cross R. So we take ordered pair of real numbers. Okay, so this set, it is the collection of say xy such that, or let me write it as x1 x2. So it's easier to generalize in that case. So it is the collection of x1 x2. So x1 is the first coordinate, x2 is the second coordinate, such that x1 comma x2, these are real numbers. Okay, so we take collection of points in the xy plane. Okay, so it means geometrically this is nothing but the collection of points in xy plane, right? So in your school days itself you have done, say this is 1, this is 2, this is 3, this is 4, right? 1 2 3 4. Okay, so if I want to mark the point say 1 comma 3, okay, so 1 comma 3 will be a point somewhere here. Okay, so this point is 1 3, right? If I want to mark the other way 3 1, so x coordinate is 3, y coordinate is 1, so the point is somewhere here, this point is 3 1. Okay, so you see that 1 3 and 3 1 are different thing. Okay, they are not the same, they are different points. So that is why this is called a set of ordered pairs of real numbers. Okay, of real numbers. Pair because there are two components here, or two coordinates here, first coordinate, second coordinate, and ordered because the order is important. You cannot change the order of this elements or the entries, okay, or the coordinates. If you change the order of the coordinates, the point actually changes, except for the case when the coordinates are equal. Say 1 1, if you change this one and this one, this remains the same. Okay, so that's not a problem. So writing 1 1 and writing 1 1 is the same thing, no? Whether you write this one or this one, it's one only. So for that there is no problem. So when x1 is not equal to x2, in that case if you change the order, then you are getting a different point. Okay, so that is why this is called set of ordered pairs. Okay, so this has also got a different name. That is also called set of ordered two tuples. Okay, I'll tell you why we are introducing this tuple here. Otherwise, because the English language is not sufficient to accommodate all terms of mathematics, right? You will see very soon. Say R3. What is R3? It is the set of x1 x2 up to x3. So 3 coordinates are there, where x1 x2 x3, so these are in real numbers. Okay, so that is what, so this is called the set of ordered triplets or triples. Okay, so the triplets of real numbers. Okay, or if I go by our mathematical notation, it is the set of ordered three tuples of real numbers. Okay, real numbers, right? R4 will be, so here R3 geometrically it represents this the space, three-dimensional space. Okay, three-dimensional space where there are 3 axes, coordinate axes, and any point on the space can be represented by 3 coordinates, x1 x2 x3. Okay, so x1 is the so if we drop a perpendicular from this particular point to the axis, okay, so the point where it intersects this plane, if I draw a line parallel to this, okay, right, if I draw something like this, okay, so this point is actually say this is the x1 coordinate, or x1 axis, and this is the x2 axis, this is the x3 axis. Okay, so this length will be your x1, this length will be x2, and this height will be x3. Okay, so this geometrically a point on space is represented that way. So further, if we generalize more, okay, because we are working with n variables, okay, so we need some theory or structure on n variables also. So x2, x3, x4, it is the collection of ordered 4 tuples. Okay, I don't know what is it called in English, maybe quadruplets or what, something like that. That's why I said our knowledge of English will not be sufficient to accommodate all this pairs, ordered, sorry, not pairs, all these tuples, because every time we have to give a new name to these things. Okay, so if there are 5, we may call pentaplets, or I don't know what it is. So mathematicians decided not to wait for English. Let us adopt our own word, so that we can we are never short of words. Okay, so set of ordered 4 tuples. So if there are 4 such coordinates, we say these are 4 tuples. Okay, if there are 5 coordinates, we will just say 5 tuples. We will not search the dictionary to find out what is that word. Okay, so in particular for the case of R2, we just say ordered pairs. Okay, so it's very easy to say pairs. In general, all these things are taken as tuples. 6 tuples means there are 6 coordinates. Okay, means we are talking about r to the power 6. Okay, so r to the power 6 is basically r cross r cross r cross r r cross r. Okay, so 6 times. So we are taking Cartesian product of sets. Okay, so that is actually 6 tuple, right? So in general, we write this one as r to the power n. It is the set of ordered n tuples. Okay, so that means there are n coordinates here, x1, x2 up to xn. So as that, so we write it this way: xi belongs to r for all I equal to 1, 2 up to n. Okay, so each coordinate is a real number. Okay, so this is called the set of ordered n tuples. Okay, n tuples of real numbers. Okay, so this is our set. Now we will try to define some operations on this set. Okay, already we have the idea of matrices. Okay, and we can define some operations on this set. Say addition. How do we add 2 n tuples? Okay, how do you subtract 2 n tuples? Okay, so let us define. So any point in r to the power n, okay, will be called a vector. Okay, will be called a vector. Okay, and any number in R will be called a scalar. Will be called a scalar. Okay. So we define 2 operations on r to the power n. Okay, we define 2 operations on r to the power n. Okay, so number 1 operation is the vector addition. Okay, vector addition, right? Vector addition. If we take say for x1, say x, let us write it, this one is x is equal to x1, x2 up to xn, comma y equal to y1, y2 up to yn. Inside r to the power n, we define x plus y as what? X plus y is x1 plus y1. So just coordinate wise we add them. Okay, so it's the natural way of adding x1 plus y1, x2 plus y2, okay, x3 plus y3, up to xn plus yn. Okay, so that's how we define vector addition. Okay, x plus y is thus just the component wise or coordinate wise sum of these 2 points, right? And number 2, we define something called scalar multiplication. Scalar multiplication. So for that we take for alpha in R, okay, and x equal to x1, x2 up to xn in R to the power n. Okay, we define alpha x as alpha x1, so we multiply each coordinate by alpha, okay, alpha xn, right? So observe that this x plus y, this is also an element in R to the power n. Why? Because each of these are real numbers. x1 plus y1, x1 and y1, they are real numbers, so their sum is a real number. Okay, we have already seen. So each of these are real numbers and they are n in numbers. Okay, so this is also an element of R to the power n. Here in the scalar multiplication also, alpha x1 is a real number, alpha x2 is a real number, alpha xn is a real number. Every coordinate is a real number. So this is an element in R to the power n only. Okay, so the operations that we have defined, these are actually binary operations. Binary operation means it is a function from, so this vector addition, it is a function from R to the power n cross R to the power n to R to the power n. Okay, so it takes 2 elements from this R to the power n and gives us a element in R to the power n only. So it's a binary operation. Okay, or that is plus is closed in R to the power n. Okay, right? And this scalar multiplication also, it's a binary operation. It's an operation of this type. It's closed. Its dot is a operation from R cross R to the power n to R to the power n. Okay, so it's a it takes one element from R and one element from R to the power n and gives us an element in R to the power n. Okay, so these 2 are binary means operations which satisfy the closure, which are closed in R to the power n. Okay, right? So under these operations we will see that the set R to the power n satisfies some special properties. Okay, so geometrically what does it mean in R? Means since the name is vector addition, you might be thinking there is some relation with vector which we have done in higher secondary. Yes, of course there is a relation. In fact, it is motivated from there itself. Say in R square, if I want to denote 2 points, okay, say let us denote 2 points or vectors. So in your higher secondary you had done something called position vector, right? Say I have these 2 points, okay, but I need to change it a bit. Yeah. Say I have these 2 vectors. Yeah. Right, so this is the point, say A, this is the point B. So there are 2 points here which have this position vector. So let me write it in red. These are the 2 points. Okay, so we have position vector OA. OA is the position vector of A and OB is the position vector of B. Okay, OB is the position vector of B. Okay, so how do I add these 2 vectors? In order to add these 2 vectors, okay, OA and OB, how do I add? So in your this higher secondary you had already done the parallelogram law of vector addition, right? So we extend this to parallel to one of the vectors, okay, and through B we take it parallel to say OA, okay. So then the resultant that we get, then the diagonal that we get is the sum of these two vectors, okay, right? That was the system, if you remember. This is the system. Now let me just give it coordinates x1, x2, and this B is actually y1, y2, okay. So what are the coordinates of this sum, okay? So in vectors itself you have done, of course, in a different notation, x1 I cap plus x2 j cap, you wrote it this way. This is the x vector, okay, position vector of x, and say this is y vector, is you had written it as y1 I cap plus y2 j cap, and immediately the sum was x vector plus y vector. The sum was taken as this wise, coordinate wise sum, x1 plus y1 I cap plus x2 plus y2 j cap, okay. This was the sum. So the coordinates of this point is actually x1 plus y1, x2 plus y2, okay. So how do I show it? It's quite simple. If you just join this two, we know diagonals of a parallelogram bisect each other, okay. So what is this point? The midpoint here. You just use your knowledge of Cartesian geometry. X1 plus x2 by 2, y1 plus y2 by 2, okay. So this is the midpoint, say D is the midpoint of this A, B, C, okay, OC and AB. So D is the midpoint. So what are the coordinates of C then? D is also the midpoint of OC, because the diagonals of a parallelogram bisect each other. So this is just x1 plus x2, y1 plus y2, okay. So that is the natural way of adding vectors, okay. So this was carried over to our general r to the power n also, okay. So in r cube also we added that way. So we have already done x1 I cap plus x2 j cap in vectors. You had already done this x3 k cap, okay. So if I take the sum of this with another vector, say y1 I cap plus y2 j cap plus y3 k cap, then the sum will be x1 plus y1 I cap plus x2 plus y2 j cap, like that, okay. So that will be the sum. So here in r to the power n also, this basically gets carried over, okay. That is how we define sum in vector addition in r to the power n, okay. So one thing you note, the properties, some properties are there for the vector addition, that if I have two vectors, say x equal to x1, so let us write this as properties, okay. So let x equal to x1, x2 up to xn, y equal to y1, y2 up to yn, okay, and z equal to say z1, z2 up to zn, okay. So be r to the power n, okay, r to the power n, and alpha comma beta, they are scalars, okay. So number one property is that x plus y is equal to y plus x, okay. It's commutative, okay. This is commutative, you can just easily verify. So this property, vector addition is commutative, x plus y is same as y plus x, okay. So if you take any two vectors in r to the power n and add them, whatever way you add, you are getting the same result, okay. Then you have the associative property, x plus y plus z will be same as x plus y within bracket plus z, okay. So vector addition is associative also, okay. So all this can be proved just using the definition of this, okay. So we don't require the proofs here, it's required in linear algebra course, okay. So the past students already you had done linear algebra, and honor student we will get linear algebra in this semester, so don't worry. we will require just this addition concepts here. For our LPP, we will just require simple addition concepts. And so there exists an element, or there exists additive identity. Okay, additive identity. What is that additive identity? A vector which when added to other vectors will give you the vector itself. Okay, 0 0 0. If I take all elements as 0, okay, so let us write it as 0 bar. 0 bar, let us write it as this, which satisfies what? Such that any element x added with this 0 vector, it will give you the element x itself. Okay, for all x inside r to the power n. Okay, so this is the additive identity in r to the power n, right? All zeros. So this is the 0 vector. Okay, then we have existence of inverse. Existence of additive inverse. Okay, additive inverse, right? So for x equal to x1 x2 up to xn, we have, say, minus x1 minus x2 up to, means if we replace every coordinate by the opposite in sign, okay, by the coordinate opposite in sign, this is also an element of r to the power n. Okay, we have this is in r to the power n. So let us denote it as minus x. Okay, then x plus minus x, this is nothing but 0, because it is a 0 vector, right? X plus minus x1 plus minus x1, that will be 0. X2 plus minus x2, that is 0. So each coordinate will become 0. Okay, so this is also equal to minus x plus x, right? So this is the existence of additive inverse. So for each element in r to the power n, we have its additive inverse. Okay, what is that additive inverse? It is just minus x. Okay, then there are some other properties as well. Number 5, it is alpha times of, or alpha plus beta times of x. This is same as alpha x plus beta x. Okay, so this is always same. So scalar, this plus is the addition of real numbers. This plus is the vector addition. Okay, you have to understand this, right? So how did I get it? Alpha plus beta of x. X is what? x1 x2 up to xn, right? So by definition of scalar multiplication, it is alpha plus beta of x1, alpha plus beta times of x2, okay, like that, alpha plus beta times of xn. Okay, so immediately I can apply, because these are the real numbers, I can apply the distributive property of this multiplication over addition. So it's alpha times x1 plus beta times x1. This is alpha times x2 plus beta times of x2. Okay, and then alpha times of xn plus beta times of xn. Okay, so this way we can do, and then apply the vector addition rule. So it is alpha x1 alpha x2, so we can separate them, alpha xn plus this is beta x1 beta x2, okay, up to beta xn. Okay, this one. So this is actually alpha into x1 x2 up to xn, and plus beta into x1 x2 up to xn. Okay, so this is alpha x plus beta x. Okay, so alpha plus beta into x will be alpha x plus beta x. So we have the distributive property. Then alpha into x plus y. So here you see this plus is the vector addition, will be alpha x plus alpha y. Okay, so this is also true. Number 7 is alpha into beta x will be same as alpha beta into x. Okay, so we can take the scalars outside. Okay, we can multiply scalars separately and then multiply it with the vector. Okay, so this is another one. And 1 into x, if we take the number 1 and multiplied it with x, this is always equal to x. Okay, so this is also one of the properties, right? 1 into x is always x. So this is for all x in r to the power n. Okay, so these are the properties. So with these above properties, so r to the power n with the above properties of vector addition and scalar multiplication, vector addition and scalar multiplication, is called a vector space. Okay, so it is called a vector space. Okay, over R, because we are taking the scalars from the set of real numbers. Okay, so r to the power n with the above properties of vector addition and scalar multiplication is called a vector space. Okay, so it also has got a special name, r to the power n. We will call it to be Euclidean space. Okay, but before that we will require the concept of distance between 2 points. Okay, once we define the distance between 2 points, we will have something called Euclidean space. Okay, right. So we define, so for x equal to x1, x2 up to xn, and y belongs to y equal to y1, y2 up to yn in r to the power n, we define the distance between x and y, distance between x and y as, so we denote it as a mod of x minus y, right, d of xy, or d of xy equal to root over. So if you recall, what is the distance between 2 points in this r square, y1, y2? What is the distance between these 2 points? Is x1 minus y1 square plus x2 minus x2 minus y2 square under root, right, root over of this 2. Okay, so this here also the distance is actually something like this: x1 minus y1 square plus x2 minus y2 square plus dot 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 up to xn minus yn square. Okay, so this actually gives us a distance between, means why it is called distance, because it satisfies all properties that is satisfied by usual distance. The distance between 2 points. What are the properties of distance? Say if I have 2 points A and B, the distance between A and B is always non-negative, greater than or equal to 0. Okay, then the distance between A and B is same as distance between B and A. Okay, this is another property. Another property is that if the distance between A and B is 0, then A and B has to be the same point. Okay, A should be equal to B. And another most important property that is satisfied is the triangle inequality. Distance between 2 points A and B is less than or equal to distance between 2 points A and C plus distance between C and B. Okay, so these are the basic 4 properties with which a function is said to be a distance function. Okay, so all these are there in mathematics, so we don't require this. I'm just telling you that this, if we define an expression this type, okay, it satisfies all the properties of the distance function. That is why this is taken as a distance between 2 points x and y. Okay, so R to the power n vector space together with this distance function, it forms what is called Euclidean space. Okay, so we say that is Euclidean space. Okay, so we denote this by of course we'll denote this with modulus only, this convex sets. Yeah, just let me verify. Yeah, Cx equal to z. Yeah. Okay, so we denote this way by e to the power n. Okay, e to the power n is the n dimension Euclidean space. Okay, n dimensional Euclidean space. Euclidean space. Okay, so they are called Euclidean space because means many of the properties of the Euclidean geometry, the plane geometry that we do, are carried over into this type of generalized structure. Okay, so e to the power n, so it is nothing but r to the power n, the vector space r to the power n, together with vector addition, scalar multiplication, and the distance function. Okay, and the distance function. Okay, why we say distance function? Distance, so it's means I had written it as d of xy or mod of x minus y. Okay, so it takes two elements from this distance function. It takes two elements from r to the power n. Okay, and gives us an element in what? It takes two elements from r to the power n and gives us a distance or element in 0, infinity. That is positive, non-negative real numbers. Okay, this is the distance function. So r to the power n together with vector addition, scalar multiplication, and the distance function is called Euclidean space. Okay, Euclidean space. Okay, so we denote it as e to the power n. Right? Clear? So we will study some properties of vectors in Euclidean spaces. Okay, something called convex sets. Okay, so for the study of convex sets in r to the power n or e to the power n, we need the concept of this vector addition, scalar multiplication, as well as the distance function. Okay, right? Okay, so for today these things are sufficient. Let us meet another next day for the next lecture.